Hey everyone, and welcome to The Explainer. Today we are tackling some absolutely crucial concepts: measurement, precision, and exactly why our modern machines desperately need human intelligence. I mean, we've all been there, right? Punching numbers into a device and just completely trusting whatever massive string of digits pops out. But today we're going to learn how to tame that machine and actually speak the true language of science. Okay, let's dive into this. Think about some standard everyday items for a second: a ruler, a pencil, an eraser. Whenever we measure something in the physical world using devices like these, we are inherently dealing with limitations. A ruler can only get you so close to the true length of an object, right? The physical world of measurement absolutely requires human interpretation, because absolute perfection, it just doesn't exist when we're relying on physical tools. We always have to make an educated guess. And, well, that leads us to a pretty fundamental problem. Check out this quote: "Our calculators are mindless drones and don't know the correct answer." It sounds a little harsh, sure, but it's actually completely accurate. Your pocket calculator doesn't understand the physical limitations of real-world measurements. It has literally zero grasp of the inherent error of the universe. It just crunches digits without context, assuming everything is perfectly absolute. So we have to step in and provide that missing context. So here's our roadmap for The Explainer today. We're going to cover exact versus measured numbers, the four rules of zeros, scientific notation and rounding, and finally, rules for math operations. Think of these four steps as your essential toolkit to outsmart that mindless drone calculator. Section 1. Exact versus measured numbers. As it turns out, not all numbers are created equal in the eyes of science. There is a really strict binary contrast here. On one hand, we have exact numbers. These carry infinite importance and absolute certainty. You get an exact number when you're counting discrete objects, like, say, counting exactly 4 pizzas in a room, or when you're using a defined relationship, like knowing that 1 foot is exactly 12 inches. There's zero doubt there. But then, on the other hand, we have measured numbers. Whenever you use a physical measuring device, your number is going to contain some error. You are literally forced to make an educated guess on the very last figure of your reading. And the crucial takeaway here is that when you plug these measured numbers into a calculator, your final answer can only ever be as accurate as your absolute worst measurement. Section 2. The four rules of zeros. Now, while digits 1 through 9 are always significant, zeros are tricky. To keep our measurements scientifically honest, we have to enforce 4 specific rules. Let's look at Rule 1. Zeros in the middle of a number are treated just like any other digit. They are always significant. If a zero is trapped, just sandwiched between other non-zero digits, it is unequivocally important to the measurement. For example, 94.072 grams. Because that zero is securely wedged right in the middle, it counts. That gives us a total of 5 significant figures for that measurement. Okay, Rule 2. Zeros at the very beginning of a number are not significant. They act only to locate the decimal point. Basically, you can think of leading zeros as simple placeholders that don't actually add any precision to the measurement itself. So in a value like 0.0834 centimeters, those first 2 leading zeros, they don't count at all. We only have 3 significant figures in this specific example. Let's move to rules 3 and 4. These govern end zeros, also known as trailing zeros. And honestly, this is where we see the immense power of the decimal point. Rule 3 says if there's a decimal point anywhere in the number, zeros at the end are automatically significant. Science just assumes you wouldn't bother to write them down unless they meant something highly precise. So 138.200 meters has 6 significant figures. But Rule 4 tells us that zeros at the end of a number without a decimal point are entirely unclear or just implied. We really can't tell if they're actual hard measurements or just placeholders indicating a large scale. Now, what's really fascinating is how that decimal rule plays out in practice. Take a number like 48,000 and put a decimal point right at the end of it. Because of that single tiny dot, every single trailing zero counts, giving us a highly precise 5 significant figures. But take that exact same string of numbers, 48,000, without the decimal point, suddenly those trailing zeros don't count at all, and we are left with just 2 significant figures. It's wild, right? Merely adding a decimal point completely transforms the precision of the message you're sending. Section 3, Scientific Notation and Rounding Rules. So how do we tame the excessive digits our calculators display? Let's look at a highly practical problem.
The distance from the Earth to the Sun is an astounding 150 million kilometers. But what if our scientific instruments only allow us to state this distance to exactly two significant figures? How on earth do we write a massive number like 150 million with just two significant figures without completely losing the grand scale of the number itself?
Well, we use the scientific notation hack. 150 million kilometers, limited to two significant figures, is simply written as 1.5 times 10 to the 8th power. This brilliantly solves our problem. It isolates the significant digits, the 1 and the 5, from the sheer magnitude of the number, which is cleanly handled by the times 10 to the 8th. It gives us perfect, undeniable control over exactly how many digits are significant, erasing any ambiguity.
We also desperately need that kind of control when our calculators inevitably feed us an answer with, say, 8 decimal places, when our original measurements only justify keeping 3. To fix this, we follow a few straightforward rounding steps. Step 1. Decide how many digits you are allowed to keep based on the rules we just learned. Step 2. Look carefully at the first digit you are removing. If it's 4 or less, just drop it and all the following digits. Step 3. If that first removed digit is 5 or greater, you round up by adding 1 to the last digit you're keeping. But here is a crucial warning. Your final rounded number absolutely must retain the same value scale as the original. If you are rounding 128,522 down to 3 significant figures, it becomes 129,000. You don't just write 129. If you did that, you'd mathematically shrink a massive value down to almost nothing.
Section 4, Math Operations. So what happens when we start combining these educated guesses? We actually have to take two very different paths depending on the exact math we're doing. For multiplication and division, the hard rule is that the lowest total significant figures wins out. You count all the sig figs in your starting numbers, and your final answer gets clamped down to match whichever number had the fewest. But for addition and subtraction, completely different story. Here, we completely ignore the total significant figures. Instead, the lowest number of decimal places wins out. You basically line up the decimals vertically and chop off the answer at the least precise column. Let's walk through a mixed operation to see this in action. Say we have numbers being added together inside parentheses, and then those separate results are being multiplied. In critical, multi-step calculations like this, human intelligence dictates that we must follow the order of operations and track our significant figures along the way, but we must wait to actually round off the numbers until the very end of the calculation. Ultimately, our raw calculator drone answer of 2179.692 rounds properly to exactly 2180 with a decimal point. Doing it this way ensures we don't accidentally introduce compounding rounding errors halfway through our math. So, to wrap up this explainer, I want to leave you with a profound question to ponder. What would actually happen in a critical engineering or science project, say building a massive suspension bridge or calculating a delicate medication dosage, if we just blindly trusted the mindless drone calculator without accounting for real-world measurement error? A tiny misinterpretation of precision can lead to a catastrophic failure in the physical world. Taming the machine isn't just some abstract math exercise, right? It's about gaining a deep working respect for the precise language of science. Thank you guys so much for diving into this with me, and remember, always question the numbers.